Hey everyone. In this video, I'm going to review some of the key concepts in causal inference, okay? And so far in this course, we've been interpreting regression coefficients and running regressions in a purely predictive sense, okay? So basically what we considered was, given the values of several inputs, our estimated model ultimately allowed us to predict our outcome measure, okay? Usually that outcome or that data set came from some unknown population, and so we characterized uncertainty around our predictive estimates, okay? The key here is that these predictions, also when we estimated first differences and so on, those were always comparisons across different combinations of values or different observations, right? So we always try to emphasize, whenever we're interpreting coefficients, to emphasize that this is a comparison between different groups of observations and how they, how the average outcome differs between those two groups, okay? And now we go basically one step further. So now we are going to consider causal inference, and in causal inference, we're basically asking what if questions, okay? What would happen to an outcome Y for a specific observation as a result of a treatment or some kind of intervention, okay? And obviously that is a much more, we need a lot more assumptions to ultimately make this type of causal inference, rather than making a pure predictive comparison, okay? And so that's what we're going to focus on today, okay? As I kind of already indicated, when we're thinking about causal questions or causal effects, we're ultimately talking about comparisons between hypothetical scenarios, okay? And this is usually conceptualized in the potential outcomes framework, okay? The potential outcomes framework basically formalizes this fundamental question of what would have happened if a certain observation received a treatment or some intervention, and what would have happened if that observation hadn't received that treatment, okay? So basically the way we can kind of think about this is that for any given observation, we have a two potential, if we have a binary treatment, so one treatment and one control group, so to speak, we have essentially two potential outcomes, and those are the values of our outcome measure, okay, under the assumption or under the condition that that observation would have received the treatment. This is here the second column, or if that person hadn't received the treatment or had received the control, okay? So that's the second element, y1, 0. Okay, the parentheses here, 0 and 1, in both cases indicate the treatment status, whether that observation has received the intervention versus not, okay? So given this kind of framework of hypothetical outcomes, okay, we can then ultimately define the causal effect, right? The causal effect, as we understand it, is based on this within-person comparison between the treatment, the potential outcome for the treatment, and the potential outcome for the control, right? So we can basically identify or define the causal effect for individual I as the difference between both potential outcomes y1 and y0, okay? So in essence, for each individual observation, we have one individual treatment effect, which is the difference between the potential outcome for the treatment and the potential outcome for the control, okay? Then we can define different types of average causal effects, right? Obviously, we're not just interested in characterizing, or we're not even able to characterize individual treatment effects, but what we're ultimately interested in is estimating average causal effects. So across all individuals, what is the expected effect of the intervention? How much does it change the outcome in one way or another, okay? So kind of based on this potential outcomes framework, we can of course compute the average causal effect by just averaging over all our taus, okay? So here the expectation of tau I, that's the average causal effect or the average treatment effect, is just the average of our tau i's, okay? And each tau I, of course, is the difference between our potential outcome in the treatment group and the potential outcome in the control group. So yi1 minus yi0. And we can separate the sum. So we have the average value of potential outcomes in the treatment group and the average value of potential outcomes in the control group. And the difference between those two is then the average causal effect or the average treatment effect. Okay? All right, so far so good. There's obviously one huge problem, and that problem is that we cannot observe both the factual outcome, whether it's treatment or control, and the counterfactual. So the hypothetical outcome of what would have happened to our outcome if that observation had received the treatment rather than the control, or the control rather than the treatment, right? And this is what is called the fundamental problem of causal inference. The fundamental problem of causal inference is that only one of the two potential outcomes for every one individual observation is observable, okay? So rather than having this full table of potential outcomes and taus that we can look at in this nice theoretical table, for each observation, we only have one realization. We only see the realized outcome in the control group if that person was actually, or if that observation was actually assigned to the control group, or for the treatment group if that observation was actually assigned to the treatment group. We are not able to observe both potential outcomes, the factual and the counterfactual. Okay? So that is ultimately what causal inference is then all about, right? Causal inference is about finding a credible way to infer the unobserved counterfactual outcomes, right? Making the people in the control group where we observe the realized control outcome and the people in the treatment group where we observe the realized treatment outcome as comparable as possible so that we can actually infer this average treatment effect that we're interested in, which is this average over our taus. But we cannot observe all the taus. We only observe these individual realizations, right? So we have to find a way to kind of infer these remaining these missing counterfactual outcomes, right? And this is why we can kind of frame causal inference in as a prediction task to a certain extent, because ultimately what we're trying to predict is these counterfactual outcomes that we don't observe, right? The treatment outcome for person 1 or the control outcome for person 2 in this case, in order to estimate our treatment effects, okay? So now the next question is, of course, what are the potential strategies to figure out these counterfactuals and to basically identify our treatment effects? And as I mentioned, they're kind of different, either design-based strategies and statistical adjustment or based strategies for observational data that we can use in order to kind of make treatment and control group as comparable as possible. Okay, ultimately, causal inference always rests on whether these identification assumptions are plausible. To what extent, either by design or by statistical adjustment, we achieve a balanced comparison between the treatment group and the control group. Okay, and of course that is a lot more challenging to kind of satisfy these identification assumptions than just the pure predictive task of just comparing different types of units without giving it a clear, causal interpretation. Okay, so one of the ways, as I mentioned, there are two different kind of strategies. One is design-based, so basically collecting data in a way that allows us to compare treatment and control group. And the other one is based on statistical adjustment, where we have, some data and we're just trying to include control for potential confounding factors and so on in order to get as close as possible to this causal inference or this causal identification. Okay, in this week we're going to talk about design-based inference, so we're going to talk about experiments. And in the next week, we're going to talk about causal inference using observational data and what kind of techniques are available to us if we don't, if we're not able to actually run an experiment. Okay, so as I mentioned, now we're going to talk about experiments or randomized controlled trials, and those are and we'll start with those because those are essentially kind of the gold standard in causal inference, okay, because they are the cleanest way of achieving this balance between our treatment group and the control group. Okay, so the key idea behind randomized controlled trials or randomized experiments is that randomization of the treatment, so whether certain observations are assigned to the treatment condition or assigned to the control condition, if we randomize this assignment, then in expectation, the treatment and control group will be identical on all possible, confounding factors, on all other characteristics that might influence the outcome or that are correlated with the potential outcomes. Okay, those should be equally distributed across treatment and control group, and then by having this balance across treatment and control group, we can then ultimately attribute any difference that we observe between both groups to the intervention itself. Okay. So in other words, if we have randomization and a large enough sample in our experiment, then the treatment and control groups are similar in terms of all both observed and unobserved characteristics. So we can attribute the average differences in outcome to the difference in the treatment. Okay. So in other words, doing this kind of formally, under random assignment, what we can say is that the potential outcomes as well as other characteristics are independent of treatment assignment. That's TI. Okay, so there's no imbalance. These are the treatment is ignorable in the sense that we knowing the treatment gives us no information about other characteristics of that individual observation. Okay. If that is the case, if the potential outcomes and any other characteristics are independent of the treatment, then one thing that we can say is that the potential outcomes in the treatment group on the left here, for people who are assigned to the control, these are basically the potential outcomes that we cannot observe because of the fundamental problem of causal inference, but we know that the expectation of those is equal to the expectation of the potential outcomes in the treatment group that we can observe, or the factual outcomes. Here we have the expectation of y1, so the potential outcome in the treatment group, for those observations that were actually assigned to the treatment group. Here we have the potential outcomes for observations for the treatment group among observations that were actually assigned to the control group, right? If treatment assignment is independent of these potential outcomes, then both of these expectations are equal, and they're just equal to the expectation of our potential outcome in the treatment. Okay, and the same holds for the control group. Here we have the expectation of the potential outcomes for observations that were assigned to control, here for the observations that were assigned to treatment, and those potential outcomes are equal because treatment assignment is independent of the potential outcomes themselves, and so we can basically and so they're basically equal to the overall expectation of the potential outcomes in the control. Okay, why is this important? Well, if we go all the way back to our average causal effect, remember that here we defined our average causal effect as the expectation of our taus, which we then separated into the expectation of our yi1s and our yi0s. But the problem was, of course, that a lot of these yi1s and yi0s were unobserved, right? This is the fundamental problem of causal inference. We don't see all of those potential outcomes, right? So we cannot directly compute this average causal effect or this average treatment effect. But if this condition holds, then we can basically replace this expectation of yi1 or this expectation of yi0 with the expectations that we can actually observe, which is for the treatment group, this expectation right here, and for the control group, the expectation right here. So essentially, under random assignment, treatments are independent of the potential outcomes. That means we can basically just average over the factual outcomes that we observe in the treatment group and in the control group in order to identify and estimate our average treatment effect. So in other words, we can express under these assumptions, under random assignment, we can express the average treatment effect as the difference between the expectation of y1 conditional on the treatment group or being assigned to the treatment group minus the expectation of y0 conditional on being assigned to the control group. And that is just the difference in means estimator, essentially just computing the difference between all the outcomes that we observe in the control group and all the outcomes that we observe in the treatment group. Okay. Now, there are a couple of crucial assumptions when we're making causal inference in the context of experiments, but also beyond. And some of those, and those are also discussed in our readings. So I just want to kind of mention them really quickly. The first one is ignorability. And ignorability implies that the treatment assignments are statistically independent of the subject's potential outcomes. Okay. Ultimately, that is kind of guaranteed by random assignment, right? That's kind of the problem that we discussed previously. To basically identify, to balance the treatment group and the control group, we achieve ignorability. Okay. Yeah. So the violation of ignorability, that means there's some imbalance in the treatment group and the control group, and that ultimately induces selection bias. You can think of this as potentially certain types of individuals selecting into receiving the treatment. Those types of individuals are or observations are systematically different than those who select in the control group, and thereby we're not only observing, by looking at the difference between treatment and control, we're not only kind of looking at the effect of the intervention, but we're also kind of capturing these systematic differences between people who selected into treatment and who selected into control. Okay. Next, we have excludability. Excludability means that potential outcomes respond solely to the receipt of the treatment, not to the random assignment of the treatment or any indirect byproduct of random assignment itself. Okay, so this can be violated, for example, if we have different procedures that are used to measure outcomes in the treatment and control groups, or if any of the research activities or other treatments or third-party interventions other than the treatment of interest differentially affect the treatment and control groups. Okay, so what is meant here is that there might be other additional kind of factors that are changed between the treatment and control group, so that we cannot kind of attribute the treatment effect itself only on the intervention. Okay, so for example, if we have some experiment that we're running in a school and we assign some classes to a treatment group and some classes to a control group, we could, potentially, if, teachers are aware of the treatment assignment or something like that, and not only kind of implement the treatment, but also implement additional measures that were not part of our actual planned intervention, that would be a violation of this excludability assumption. Okay. The next really important assumption is non-interference, or SUDVA, which stands for Stable Unit Treatment Value Assumption. And this basically means that potential outcomes of observations or observation I reflect only the treatment or control status of observation I and not of other observations. Okay, so this could be violated when subjects are aware of the treatments that other subjects receive. The treatments may be transmitted from treated to untreated subjects, or the resources used to treat on one set of subjects diminishes resources that would otherwise be available to other subjects. Okay, so the classic example would be if you have people in a lab experiment and they have different conditions. Maybe they have to read different types of information. Each of them have to read a different news article, for example, but they sit all next to each other and they're able to see the other person's news article or something like that, or they just look at some pictures or something like that, right? So then you have a violation of this SUDVA assumption, because the treatment assignment, the person who was, assigned to a certain story or a certain picture, then views the other individuals, the other participants' treatment, so to speak, and thereby you have interference between both of those treatment assignments. All right. So those are crucial assumptions for causal inference that we should take into account, particularly in when designing and analyzing experiments. But they also play a role, of course, in the context of causal inference with observational data. Okay. The last thing I want to mention, there are a couple of additional considerations to take into account when we talk about causal inference in experimental settings. One is that we talked so far. I just talked about basic average treatment effects or average causal effects. Okay, but of course, this average causal effects or these since the individual causal or since the causal effect varies by person, by individual observations, right? We had different tau i's basically. That ultimately means that any definition of an average causal effect will also depend on what group of people we're averaging over. Okay, so depending on who you're averaging over, you'll get a different average causal effect. Okay, so that means that we can also think about different types of causal effects, right? By basically averaging about different groups of people. Okay, so the first kind of average causal effect that we talked about so far is the sample average treatment effect. Okay, and this is just basically the average effect across all observations that are included in our sample. Okay, we can also examine and check conditional average treatment effects. So basically, here we're calculating the average treatment effect for well-defined subsets. Okay, so for example, we would like to compare treatment effects between men and women, or between people in one education group and in another education group, or something like that, right? So then we would kind of just average over those subsets of observations to compute average conditional average treatment effects. Okay, and then last, one thing that we haven't the one thing that we talked about in the past when it came to kind of like representativeness and surveys and probability surveys was our goal was always to kind of make inferences about a larger population, right? So to the extent that our sample for our experiment is a perfect random sample of the population, then our sample average treatment effect is also an estimate of the population average treatment effect, right? But obviously, in many cases, our sample, our experimental sample is not equal or is not representative of the population itself. Okay, so in that case, the sample average treatment effect is not equal to the population average treatment effect. But we can we talked about post-stratification already, so there are techniques of basically re-weighting our conditional average treatment effects for different groups in order to kind of provide better estimates for the population average treatment effects as well. Okay. So those are just three different kind of types of causal effects that we can think of depending on our substantive question and our theoretical interest. One might be more crucial than another. It depends ultimately on your research question itself, and there are a lot of other related types of causal effects that you might see in the literature. One thing, for example, I already mentioned compliance in the overview video. One thing that people often worry about is how to estimate basically treatment effects under circumstances where some individuals do not actually kind of take the treatment, they're not complying with the treatment assignment, and in those cases you can estimate different types of causal effects, like the intention to treat effect, which is just the effect of the treatment assignment itself, disregarding whether that person actually complied, or local average treatment effects, which are basically conditional average treatment effects, conditioning on people having received the treatment, for example. Okay, so there are more types of causal effects once we get kind of more into the depths of the experimental design and causal inference. But ultimately, the underlying idea is always we have different kind of groups of observations that we want to average over to basically characterize our causal effects. Okay. There are not only different types of causal effects, there are also different types of randomized experiments. On the one hand, kind of the simplest example is the completely randomized experiment, where we basically just have a known and equal probability, or it doesn't have to be equal, but in the simplest example it would be equal, but known probabilities of being assigned to the treatment, and it is the same for each unit in the sample. Okay, so that's basically complete randomization. Okay, in some cases it can, or in many cases actually, it can be beneficial to use what is called blocked randomization. Okay. Here we're basically not just simply randomizing across all observations, but we're randomizing within blocks. Okay, blocks are defined by certain groups or characteristics, such as gender or partisanship or other basically groups that might be predictive of the outcome itself. Okay, and so the idea here is to basically achieve two goals. On the one hand, we want to ensure that our treatment and control groups are balanced between those blocks. Okay, and on the other hand, we want to increase our precision and increase our efficiency. Okay, and randomized block designs by basically randomizing within each of those groups, within each of those blocks. So basically assigning to treatment and control within all men and within all women, or within all Republicans and within all Democrats. We basically make sure that Democrats and Republicans are equally distributed across treatment and control, and so we ensure balance, and we increase precision, and we increase efficiency in our estimates, right? So blocked randomization in many cases improves our experimental design and our analysis. Okay, then sometimes we have what is called matched pairs experiments. Matched pairs experiments are basically special cases of randomized blocks experiments, where we just have two observations within each block. Basically, you're selecting pairs and then assigning one observation to the treatment group and one observation to the control group. Okay. Again, this ensures balance within blocks and increases precision and efficiency. But of course, not every experimental design is, not with every experimental design can you employ like a matched pairs experiment. Okay. And then lastly, we have group or cluster randomized experiments, and this is, for example, the case where if we run an experiment in a school, for example, it's pretty hard to randomly assign individual students to certain conditions in the classroom. So instead, we're then randomizing by class, and so we're assigning different classes to treatment and control groups. Okay, the key here is that we have to, if we have such a group or cluster randomized experiment, we have to take into account this clustering. Okay, the easiest way is to basically treat the cluster itself as one observation. Okay, so rather than analyzing individual students, we would analyze kind of outcomes for classes, for example. Or take into account the clustering in like a multi-level modeling approach. Okay. The key here is compared to the randomized block or paired experiments, which increases balance and increases efficiency and increases precision, group or cluster randomized experiments don't increase precision. Okay, they ultimately they're ultimately like comparatively less efficient than, for example, complete randomization. Okay, but they're oftentimes necessary, as I mentioned in the school example, just due to the nature of the treatment assignment. Okay, because in the classroom, if you assigned by student, you would have issues with SUTVA violations and so on. Okay, so blocked randomization is used to improve precision and improve experimental designs. Grouped or cluster randomized experiments are a necessity due to other reasons because we're concerned about SUTVA, but they usually decrease efficiency compared to a completely randomized experiment. Okay, and again, this is an incomplete list. There are other types of randomization strategies that we can talk about more in depth as well. Okay. Summary, up to this point, we talked about prediction, we talked about correlations and predicting average outcomes, but I always try to emphasize that we cannot imply causation by through the covariates and coefficients that we ultimately estimate in our linear models. Okay, ultimately making inferences about cause effects is much more difficult and requires more assumptions. And the underlying reason is that we have this fundamental problem of causal inference. Okay, so the causal effects, just by definition, are based on the comparison between a factual and a counterfactual, but these counterfactuals are inherently unobservable. Okay, and so one of the solutions that we talked about is randomized controlled trials or randomized experiments, where we just by virtue of randomization ensure that the treatment and control groups are identical on average, and that means that they are similar in all observed and unobserved characteristics. And if that is the case, we can look at the difference in average outcomes between the groups, treatment and control group, as an estimate of the sample average treatment effect. Okay. Additional considerations come into play when we want to extrapolate this to the population and want to consider population average treatment effects. And as I mentioned, we can also look at conditional average treatment effects for specific subgroups of our sample as well. Okay. So this is a quick overview and partly review of causal inference. In the next video, I will then move on to how we can use regression or generalized linear models to analyze randomized experiments.